So thanks for the nice introduction. I want to preface it by saying that, the last years we're losing the war against machines. So machines are getting better at the things we used to be good at. And now with this talk, we want to claim one back and do something that previously only machines could do, but now we do it as humans. So this one is dedicated to all the humans in the audience. And we try to prepare a nice show for you. So let's see whether it's time to start. Yeah, that looks about right. And so you've seen in the previous talk, what we're talking about here is microarchitectural attacks. So these are attacks that occur when different security domains run on the same physical platform. We see that on laptops, phones. We obviously see that in the cloud. That's the entire business model there. And what we're going to look at is kind of where the previous talk stopped. So they said, OK, we have these L1 caches, and then you can take a further trip down memory lane. That's what we're going to do now. So if we have our CPU cores, we have different levels of caches. And the closer you are to the CPU core, basically, the shorter it takes. And what we've seen in the past is we've seen, attackers and victims on the same core. There's a lot of side channels there. First there was the L1 cache, then the L2 cache, then execution ports, and then the talk you just witnessed is also a side channel on the CPU core. So that's a move that attackers have been making. And then we've also seen, attackers move to the last level cache, so attackers can actually move across cores. But there's one thing that timing side channels need, all of them, and that's time. Okay? So what these timing side channels exploit typically is timing differences in the order of nanoseconds. So that's very, very tiny timing differences. 1 nanosecond, 10 nanoseconds, maybe 100 nanoseconds. What if we just turned all of those off? Because processors have like these fancy timers. Why would we still enable them? Can't we just turn all the timers off and then the attackers can't do timing attacks anymore? And then we're secure, right? Okay. So that's an approach that actually has been undertaken in practice. So it was first proposed academically, but then all of the major browsers actually disable fine-grained timers, and they only give you timers upwards of 100 microseconds, which is several orders of magnitudes larger than the timing leakage. So maybe we're still secure there and everything looks green. But then now, a few years ago, the fine folks at Google found out that you can actually amplify timing differences. Like these tiny timing differences, you can make them much larger and continue exploiting. But they've only kind of figured this out for the L1 cache, which still requires an attacker to be on the same core, which is not always possible. So Marton, can we kind of expand this out? Can we build a show that enables much more attacks? What do you say?
I think we can. So indeed, as Toon said, what our goal is to kind of reinstate this terrible state of affairs where an attacker was able to conduct attacks on pretty much any microarchitectural component, even if they're not allocated on the same core as the victim. So this is our goal, to be able to conduct attacks in all these different microarchitectural components. And even if we move the attacker to a different core, we still want to be able to observe these kind of secret-dependent leakages that might happen as a result of victim activity. So we identified two kind of requirements for this type of leakage to achieve this goal of exposing the secret in pretty much any component in the microarchitecture. And the first requirement for the leakage is to be visible. So this means that it needs to happen in one of these components that the attacker has access to. So for example, in this case, you see that the attacker is allocated onto a different CPU core than the victim. So the attacker doesn't have access to all the L1 and L2 caches of the victim. So we developed these so-called conversion routines that we use this magic wand to represent, which takes a leakage from one of these invisible components of the victim and translates it into leakage in one of the components that is visible to the attacker. That's the first part, but then this leakage still needs to be measurable. So the leakage usually translates to some tiny timing difference in the microarchitectural state. For example, in the previous attack, we've seen that depending on this scheduling, you might have a couple nanoseconds of execution time difference. But if the attacker only has access to a very coarse-grained timer, they still cannot measure the difference between such a tiny state being 1 or 2 nanoseconds behind or ahead of time. So as a second kind of routines, we developed these amplify gadgets that can take such a tiny difference in the timing of one of the microarchitectural states and translate it into a bigger timing difference. So with that in mind, let's zoom in on the attacker. We have these very basic attacker requirements. So as I mentioned before, we do not rely on the attacker being allocated to the same CPU core as the victim. We do not require huge pages to be enabled, which used to be a prerequisite to many other attacks or methods of amplification or simplifying attacks. And we also do not assume that the CPU frequency is fixed, which can also help simplify attack procedures. So with this in mind, we created these convert and amplify routines that only use these basic attacker capabilities. But how do these routines actually look like?
Yeah, right. So our show contains 2 tricks. We have conversions, we have amplification. So now we're going to look at amplification. So if we have a small timing difference, can we do some magic trick to make that timing difference very, very large? And so what you normally would do is if you have a timing leak, you have some kind of action, maybe a load from the cache that you want to time, and you have your fine-grained timer, and then you see, okay, if the data is in the cache, it takes, for instance, 10 nanoseconds. If it's not in the cache, maybe it takes 100 nanoseconds. But you have a fine-grained timer, so you can see the difference. Now, of course, if you have these coarse-grained timers, then this small action will not produce any perceivable difference. So we need some kind of magic trick in our show to be able to do that. And one naive thing you could think about is, why not repeat this action over and over and over and over and over and over and over again? Maybe that at some point you have a large timing difference, and then you again have your leakage. But there's 2 problems with that. So one problem is it's not always possible to repeat the same action over and over and over and over and over again. And then the second problem is these timing differences typically accumulate very slowly. So it takes a very, very long time to just do a single timing measurement. So we want to do better than that. And so what we propose in our show is a single shot amplifier. And so that basically means that you have a single action you still want to measure. Maybe it's a cache hit or miss. But you have a sequence, you have a code sequence that kind of, from this single cache hit or miss, produces a large timing difference that you can then easily pick up with your coarse-grained timer. And to understand how these work, we need to go a bit into the computer architecture. So this is a cache, which is something that many of you are familiar with. There were even questions about it just now. So a cache is a hardware component consisting of a number of sets and ways. And memory addresses are mapped to sets based on parts of their address, so the index bits. So an address that has these 3 0 bits goes to cache set 0, 5 goes to cache set 5, and so on. And then lines can be mapped to any of the ways in the set. But at some point, the cache set is full. And then if a new line comes in, something else has to go, because your capacity is finite, right? And the line that has to go, that's some kind of algorithm in the CPU that decides that. And the line that has to go, we call that the eviction candidate. And so if the new line comes in, some other line is the eviction candidate. So that one is the next one to go. We didn't think this with the previous authors, but they told us something very important, and that's that we need to study side channels like nature. And so, Marton, what's your favorite part of nature?
If I look outside, I think I already see the answer, trees.
It must be trees, yes. So let's look at trees. So our first single-shot amplifier we're going to build is going to use trees. Okay, this is a tree, that's a small tree, right? And this is going to be our cache replacement policy, so this is going to be what decides the eviction candidate, so which line to go. And if you have a small tree, you have one of the branches, you have this arrow that points to the line you want to evict next. So if a new line comes in, right, line X comes in, you're going to evict X. And then next time, if another new line comes in, the arrow moves and you would evict B. Now, trees can be bigger. Same thing holds. You have this sequence of arrows that point you to the line you want to evict next. New line comes in, and then all the arrows move basically away from the line you just introduced. And then the folks at Google figured out that if you have a tree like this, you can do something very special with this line B. And that's that if you access this line B over and over again, you kind of ensure that the arrow, the top arrow, is always moving away. And that means that this X will never be evicted from the cache, even though you never access it anymore. So this is a clear failure of the replacement policy, but nonetheless, it's something that actually occurs in decades, well, more than a decade of processors. And how you can amplify this then is, so what we want to amplify is whether there's a cache hit or miss on this X. So what we can do is, if we have a pattern BA, BC, BD, BA, these are all in the cache, so they will all be hits, so they will all be fast. But here, on the other hand, if we always access B, then we kind of reduce the size of the cache because this X will always be there without accessing it. And so now we have 4 cache lines that are competing for 3 spots, so there must be misses. And then this is something you can repeat over and over and over and over again. And then you have a nice single-shot amplifier based on, trees. We made a few improvements to the Google POCs, so increased the amplification ratio. So this one used to be only 30% slower than that one, so you still need to do a lot of repetitions. We increased that ratio to 2x, and we managed to increase the timing difference you can produce with it to 5 milliseconds. So that's already many, many orders of magnitude, which is quite nice. And then within the context of our show, we're not able to go into it right now, but we will later. We will be able to use that to amplify more side channels. Okay, so nature has trees. So maybe pointing to the audience, what's something else you like about nature? Animals.
Animals, great. Animals, what's your favorite animal? Dogs, okay, that's what I thought. So Ton explained this tree amplifier that's very nice, but as he mentioned, this works in the L1 cache. So it still has the disadvantage that the victim and the attacker need to be allocated onto the same core, and it's only events in the L1 cache that you can then amplify. So the dog amplifier, officially known as the prefetch amplifier, comes to the rescue, because this one works in the LLC, so that's the shared cache between cores. So even if the victim and the attacker are allocated to different cores, they still both have access to the LLC, the last level cache. And so if we can amplify events in there, then you can detect victim activity across cores. How does this amplifier work? It relies on a special x86 assembly instruction, which is called the prefetch NTA. And what this instruction does is it tells the CPU that I want to use a certain piece of data, I want to load it from memory, but I'm not going to use it after that. So don't bother caching it very well. What this translates to in more technical terms is that it will be loaded into the last level cache if you access a data through this prefetch NTA instruction, but it will be immediately marked as the eviction candidate. So that's going to be the next piece of data in the cache to be replaced if afterwards we load a different piece of data. How can we use this to amplify events? Let's take the example where we have 2 cache lines that map to the same set, A and B, and we want to detect the single event of whether the victim accessed A or did not access A. Let's take the example first where the victim did not access A, so A is not in the cache. In this case, what we do as the attacker is we have this little code routine running at the bottom, which continuously tries to prefetch A and prefetch B, and just does this in a loop many times over. so that you can see here at the bottom. And what this code snippet will translate to in terms of cache activity is that initially A is not in the cache. So then the first instruction will prefetch A. It will translate into a cache miss, so it will take some time to load it into the cache. And it will be immediately marked as the eviction candidate, as marked by this arrow, which means that the next value that we will load will evict A immediately from the cache. So the next load that we perform is this prefetch NTA of B. So that will also be a cache miss, because B is also not in the cache, so that again takes some time. And it immediately evicts A. So then when we repeat the loop and we load A again, then the whole process just repeats. We continuously evict A and B from the cache, resulting in many cache misses, which takes a lot of time. In the alternate scenario, where we have A already in the cache when we start, and A is not marked as the eviction candidate because it has been recently used by the victim, then the way this prefetch NTA instruction behaves is that it will load A from the cache, but it will not mark it as the eviction candidate because another process also used it recently, so it's reasonable to assume that it will be used again, even if we say that we're not going to use it again. It was already in the cache, so other people or other processes might still use it. So then that will translate to a cache hit. It will be fast. It will not be marked as the eviction candidate. And then when we prefetch B, it will be a cache miss initially. It will be loaded into the cache. It will be marked as the eviction candidate. But now comes the good part, because when we repeat this loop and we load A again, it will again just be served from the cache as it was. And then when we prefetch B again, it will still be served from the cache because we didn't access any other piece of memory in between. So even though it's marked as the eviction candidate, it's not evicted. So if we continuously access A and B, in this case, it will translate to many, many cache hits, except for this initial miss. So that will be a lot faster than all the misses. And so much faster, in fact, that the timing difference between executing this amplifier for an initial cache hit or a cache miss results in a 10 times timing difference. But there must be a catch. So in the previous amplifier, we could only do an amplification difference of 1.3, and then we improved that to 2 times. But if with this amplifier we can have a 10-time timing difference, then maybe it's not robust at all, right? Toon, can you give us an idea of how robust this amplifier is?
Yeah, sure, Marton. So let's turn this up to 11. So there's 2 promises we made. So we made the promise that this would be a show, and we also made the promise that we would center it around human beings. That's you. So we have a live demo prepared with a broken pipe. That's fantastic. But no problem. So this is actually a demo that's running on a machine in our lab in Belgium. Okay, that's quite a distance from here, you know, but with the speed of light, maybe that will work. But so maybe to fix that, what we could do is run this on a very, very sophisticated high-performance network. So I looked around in the Wi-Fi and I found this network called Eduroam, which I'm told is really, really sophisticated. And yeah, maybe that can work. So let's see whether we can have a demo running. So this is all live connected to Belgium. And this is going to involve you. So please brace yourselves. And this is what we're actually going to do is we have this very tiny timing difference, 10 nanoseconds. And what we're going to do is we're going to use our amplifier and see whether we can amplify it up to some level that maybe you as a human can see it. But in any type of timing attack, you need to calibrate first. You need to know what's a hit, what's a miss. Okay? So that's what we're going to start with. So I'm first going to show you a hit. Okay? So we saw show, we saw time, ShowTime. They appeared at the same time. That's a hit. Okay? So the demo will tell us that. Maybe this is another hit. Did you see it? Maybe you blinked and you missed it. So this was also a hit. Final hit I'm going to show you. Okay. Now let's look at a miss. Let's look at an amplified miss. So this was a hit. Let's look at a miss. Ooh. Did you see that, Marton?
Yeah, in fact, I was bored in the middle of it. It took so long.
Yeah, I almost fell asleep. So that was a miss. Let's see another miss. Okay. I think you can kind of see it, right? So we're still calibrating here. So that was another miss. In case you forgot, let me show you a hit again. Okay. So that was a hit. And this is another miss. Okay. And now it's up to you. So please brace yourselves. And I'm going to count down 3, 2, 1, and then you say hit or miss, depending on what you think it is, okay? You ready? Okay. Let's go. 3, 2, 1. Nice. Okay, 1 out of 1. Okay, let's do another one. You ready? Okay. 3, 2, 1. Oh, nice, nice, nice. Okay, third one's the charm. Let's see if we got some good karma from the demo gods here. 3, 2, 1. You've been fantastic. Wow, that's really amazing. So we tested this out with a larger sample size. Well, not larger in the absolute sense, but in the number of measurements we exposed them to. So we tested this on 15 humans. From our university, 100 samples each, and they were very willing to do so by expose themselves to 100 of these measurements and then annotating them as hits and misses. So my colleagues are really fantastic. We have an average correct detection rate of 98.4%. That's very large. I mean, some native timers don't even give you that. And some humans are even, I'm doubting whether they're human at all because they could do so with 100% accuracy. So lovely. So those were amplifiers, but remember that we had 2 tricks, right? We had an amplifier, but then we also had something else. What was that, Marton?
Conversions. So amplification is one thing, but if the leakage happens in a microarchitectural component that is not visible to the attacker, then all this show is for nothing. So how can we perform these conversions? I'm going to quickly demonstrate one of the converge routines that we developed. And this actually relies on the principle of out-of-order execution, just like we've seen in the previous talk. So I can just skip the explanation, right? Everyone is already an expert on out-of-order execution. Just to summarize in one sentence, we have programs that we run on computers, but on modern computers, these instructions that we write in this neat program order might not be executed in the same order inside the CPU, depending on their dependencies, for example. If you have a function that takes a very long time to calculate some result, and then we have 2 instructions where one of them depends on this result, but the other one doesn't, then the CPU might schedule this instruction to execute before the previous one, because that one is still waiting for the result to be finalized. Okay, that's great. Props to the engineers, but how can we use this to leak secrets? Well, we've seen one example in the previous talk, but we can kind of generalize that a little bit with this conversion. So let's say that we have a program that contains some instructions. If we have 2 dependency chains inside this program, you can even view this as kind of 2 separate legs of the same program. Because if one of them always depends on the same parameter and the other instructions always depend on a different other parameter, then the CPU can kind of execute these 2 legs in parallel. But if the timing of the 2 legs is not the same, so one of them finishes earlier than the other, and we can detect this, then, well, we know which leg finished earlier. So to make this a bit more concrete now, if one of the legs has a secret-dependent timing, so for example, there's some kind of secret that the victim operates on, and if the secret is 1, then this certain instruction or function call takes a long time to execute. But if the secret is 0, then this function takes a short amount of time to execute. Then if we can somehow measure this, then we can infer whether the secret was 0 or 1. So what we do is we construct a leg that uses this secret-dependent function. And in the other leg, we have a fixed delay that's calibrated to fall in between the long and the short time of the secret-dependent function's execution. So depending on which leg finishes first, we can tell, okay, so if the second fixed leg finished first, that means that the other leg took a long time. That means that the secret was 1. If the fixed leg finished second, then we know that the first leg finished first. It took a short amount of time, so the secret was 0. So we just need a way to be able to determine which of the legs finished first. And to give a concrete example using this prefetch amplifier that I introduced before, we can have kind of a synchronization event at the start that both of the legs are dependent on to make sure that they start executing at the same time. This can be evicting the cache line A from the last level cache. Then we have some secret-dependent operation. And afterwards, we have a load that's dependent on the secret-dependent operation. And this one just loads back A into the cache with a regular memory access. In the second leg, we have a fixed delay. But then instead of a regular load, we use this prefetch NTA instruction, so the one that marks A as the eviction candidate in the LLC. And then as the final instruction that will determine which leg finished first, we have a load of the B. So this is the other cache line that mapped to the same set as A. And what will happen is that if the first leg finishes first, so this load is executed before the prefetch NTA, A will be loaded regularly into the cache and not be marked as the eviction candidate. Then the second leg, again, uses this prefetch NTA to load A from the cache, but it will not update its status to be the eviction candidate. In the other case, if prefetch NTA is executed first, A will be marked as the eviction candidate. It will also be loaded into the lower levels of the cache hierarchy, so the L2 and the L1 caches. This other load will be served from those, from L1, for example. So it will also not update the caching status, so A will still be marked as the eviction candidate. So finally, what we are going to look at is whether this final load of B evicted A or not. Because if the prefetch NTA executed first, then A was marked as the eviction candidate. So the load of B evicted A from the cache. But if it was the other way around and A was not marked as the eviction candidate, then this load of B will also not evict A from the cache. So based on the presence of A in the cache, we can tell which of the legs finished first, and we can infer what the secret delay was, and we know what the secret was. So this is one of the conversion routines that we developed in the paper, but we actually have more. So if you're interested, you can check out our paper. It will be published at Asia CCS this year. And we have multiple examples of combining these convert and amplify routines. For example, we perform a cross-core port contention attack by combining these routines. We are able to measure the CPU frequency by using our tools. We actually have a very interesting primitive that performs a conversion, but it does not convert a given timing difference to a different timing difference in another component, but it immediately encodes that timing difference into the architecture. So you don't even need a timer at all at the end. You can just read out a given value from memory and you know what the timing difference was, or rather what the secret was. And as a final example, we also construct eviction sets. This is finding addresses that map to the same cache line, the same cache set. And this is useful, for example, for performing all kinds of cache attacks that you can then build a Spectre attack from, or if maybe you've heard of rowhammer attacks, these also rely on the presence of eviction sets. So in this eviction set, we basically take addresses in the LLC, and we try to find addresses that fill an entire cache line in a given cache set. So we performed this eviction set creation in the browser, where, as Toon already mentioned, timers are already restricted as we speak. So for example, in Chrome, in the default setting, the default protected setting, the performance.now timer has a granularity of 100 microseconds. And in this setting, we used the 3 PLRU amplifier and this time-to-order conversion to be able to construct eviction sets, and this works very well. It's, in fact, very accurate and very quick bit in brackets, but it takes about 20 seconds to construct an eviction set, which is a very realistic time to spend on a website. And then we also performed this experiment on Intel CPUs, where we used this second amplifier, the prefetch amplifier, to construct these eviction sets. We actually don't even need a conversion routine in this case. And you might be wondering, so in the browser setting, we could construct eviction sets with a timer granularity of 100 microseconds. What's the granularity of a timer natively that we can still use to construct eviction sets successfully? So we started restricting our timers arbitrarily. We started by setting a granularity of 1 microsecond, and then you can successfully create eviction sets in about 1 millisecond. Then we restricted it further and further. At one point, we got to this 100 microseconds, so the one that's the resolution of the timer in Chrome. And we could still successfully create eviction sets in about 1 second. And then we kept going, and then we kept going, and then we kept going. And at this point, it's pretty unrealistic that you would have such a restricted timer, but you can still create eviction sets with a timer that has a granularity of 100 milliseconds. It takes about an hour, but it works very well. So how far can we go? Like, can you think of a timer that's almost ubiquitous on any computer system, that's accessible from pretty much any programming language? Any idea of such a timer?
Aren't we going to have a problem in 2038 with the timer?
Yeah.
Isn't that the one?
So maybe you can only successfully create eviction sets until 2038, but you can do it. So this is the Unix epoch timer that increases every second. So it counts the number of seconds since 1970. And if you use this timer, you can still create eviction sets successfully using this prefetch NTA instruction conversion routine.
So we should nerf it, right? We should remove the Unix epoch.
Yeah, I think that's a feasible mitigation.
Yeah, let's do that. Yeah.
Can you think of, like, is there anything else we can do? Like, can we restrict this even further somehow?
One order of magnitude more. How long does that take?
That's a pretty long time. So if you have a timer that's so coarse-grained that it only increases every 10 seconds, there's no way, right? It cannot be that robust. It is. It takes about a day to finish constructing one eviction set, but you can successfully do it even with a timer that has a granularity of 10 seconds. So what can we learn from this? Is there any hope?
Yeah, so a takeaway is, probably the main takeaway is that if people try to convince you, we have all these timing side channels, there's a clear single stopgap solution, remove all the timing sources, then still you can run into issues. So if someone tells you that, it's better not to believe them and paint a more nuanced picture. So restricting timers is not a complete countermeasure against timing attacks for 2 reasons. Side channels can be amplified. We've seen them be amplified up to, let's admit it, ridiculous proportions. And then also, if you have these amplifiers, you can convert all kinds of other side channels into these amplifiers, and then you can kind of see everything again. So with that, I'd like to move on to the Q&A part of the talk, and we'd like to thank all the humans in the room for participating in our show.